Hi, everyone. So today I'm going to be talking about a broad area of science that I work on, namely short period optical variables, but with a particular emphasis on a class of gravitational wave sources that many of you may not be familiar with. These are millihertz gravitational wave sources, which will be detectable by a future space-based gravitational wave detector called LISA. And so much of the work you're going to see I did for my PhD, and it's kind of a motivation to learn technical details about things like light curve modeling, which are essential tools for characterizing these sources. So let me elaborate a bit on these gravitational wave sources to start with. For those of you who aren't familiar with gravitational waves, which I think most of this group should be, they're basically self-propagating perturbations in the space-time metric generated by the time evolution of a quadrupole moment of a mass distribution, in particular its third time derivative. The mass distributions which have such strongly evolving quadrupole moments in their third time derivative happen to frequently be binary systems involving two extremely dense objects. And the reason dense object is important is to get sufficiently large strain in the space-time metric, you need the length scales over which the gravitational perturbation happens to be quite small. And in order to make those length scales small, you need your source of mass, basically your quadrupole moment, to be concentrated into a small region of space. And so gravitational waves are basically a tool for us to study some of the most extreme objects in the universe as a result. And so you guys are probably familiar with LIGO and the types of sources it detects, but something that many of you may not have heard of are what LISA does. So LISA is a complementary observatory to LIGO in that LIGO operates at high frequencies, sort of on the order of 100 hertz, whereas LISA actually operates on the order of millihertz, so many orders of magnitude lower frequency. And so the sources that LISA will detect will largely be different than what LIGO is looking at, and vice versa. And I think one of the most exciting things about LISA is the sources that it's detecting, unlike sources that LIGO detects, will be mostly within our own galaxy. And they're also not transient events that just merge and vanish. They actually stick around for a while so that you can study them and characterize them in great detail. And that's part of what I'm going to be talking about during the remainder of this talk. But I just want to show kind of the generic characteristic strain versus frequency sensitivity diagram for various forms of detectors. And I just want to emphasize, you can see that those black curves, which are the sensitivity curves, they don't overlap for LISA and LIGO. And so what I'm going to be focusing on for the remainder of the talk in particular are these resolvable and unresolvable galactic binaries. So what are these gravitational wave sources? I mentioned they're dense objects, but they're not neutron stars or black holes, though they could be. The vast majority of them are actually white dwarfs. And for those of you who aren't overly familiar with white dwarfs, the basic story is white dwarfs are the remnants of most main sequence stars, basically anything under about 8 solar masses. They are degenerate, which means basically their electrons occupy Fermi degenerate energy levels. And their equation of state, we think we understand quite well as a result. Their composition tends to be either a helium core or a core made of carbon and oxygen as the result of fusion in their progenitor main sequence stars. And something special, for example, about helium core white dwarfs is they can only be formed through binary evolution. I can talk about that more later, potentially. But just as a sense of scale, they're on average about the size of a rocky planet like the Earth, but they have masses comparable to that of the sun. So these things are 1,000,000 times more dense than the matter that you're used to dealing with here on Earth. And so that density is an important property, and I'm going to explain why now. So here in the top panel, I'm showing basically the zero temperature mass radius relation for a fully degenerate Fermi electron gas with an electron over density of 2. And below that, what I'm showing is actually a plot of the density of the object as a function of its mass. And you can see I cut off at 1.4 solar masses, which is the white dwarf Chandrasekhar mass, and that's because white dwarfs become ultra-relativistic at that stage and end up actually collapsing into neutron stars. And that density plot on the bottom is actually really important for the following reasons. If there's a very, very useful relation, which I would urge you all to get familiar with, and it's the one that I just put up on the screen here. It says that the period at which an object overflows its Roche lobe, which basically means if an object is in a binary system, the lower density object, if you put them too close to each other, the two objects too close to each other, will begin transferring mass through the Lagrange point to the other object, just because the other object's gravity wins over this object's gravity trying to keep stuff on its own surface. And the orbital period at which that occurs is simply a property of the density of the lower density object. At least this is a very good approximation, except for extreme cases in mass ratio. For example, mass ratio is greater than 100, which you're not going to find in most of these systems. And so the relation basically says the orbital period in days at which an object will overflow its Roche lobe is approximately 0.43 divided by the square root of its density, rho, where the density is given in grams per centimeter cubed. And so you can actually translate the density of these white dwarfs into a characteristic orbital period at interaction. And if you look on the y-axis to see those orbital periods, you see they range from about 10 seconds for the highest mass white dwarfs, up to about 1,000 seconds for the low mass end. If you take 1 over those periods, those happen to correspond very nicely to the millihertz frequencies that LISA is sensitive to. And so what that's telling you is LISA is very well tuned to detect white dwarfs right about at their period minimum when they start interacting. And so there's a lot you can learn from these sources. One is that you can learn a lot about binary evolution, namely common envelope evolution, because if you find 2 white dwarfs in an orbit of just a few tens of minutes, they weren't born there. The main sequence stars they originated from are way too large to fit into such short orbits. So you had to get these 2 stars down to these orbital periods. And the processes involved there, like common envelope and also stable mass transfer, are some of the same processes that are also form other types of compact binaries, including the ones LIGO sees, because the stars that form the large black holes and binary black hole mergers did not start out in binaries orbiting at 100 hertz frequencies. They had to originate in a different way. And depending on whether you assume the 2 stars were bound in the beginning or captured through some dynamical interaction, you may encounter some of the same binary evolutionary scenarios that were necessary to produce double white dwarfs. One of the more exciting things about these 2 is when they merge, they can explode. If the sum of the masses of the 2 white dwarfs is the Chandrasekhar mass or higher, it's very possible that this results in a type 1a supernova. Basically, the degenerate matter in the white dwarf undergoes fusion, and this actually disrupts the entire white dwarf in a very important type of explosion that's actually a standard candle that led to a Nobel Prize. And I think the final thing that's interesting about them is we're not going to be talking about sort of tens of events like we are now in the land of gravitational waves. We're going to have tens of thousands of sources to work with in the LISA era. And so the population characterization one can do is just incredible, especially since the vast majority of those will be detectable in electromagnetic radiation. And so I want to shift gears and just say briefly that the way I identify these is using ZTF. And so here's a picture of Palomar Observatory. And ZTF is on that little 48-inch telescope there on the left. And it's an incredibly powerful instrument because this is an Ocean-Schmidt telescope, which means it has a very large field of view. And And that allows ZTF to basically image 47 square degrees of sky with every pointing. And that's crucial because it means ZTF very quickly can acquire hundreds or even thousands of samples across the entire sky in the span of just a few years. And using those hundreds or thousands of samples, which by the way is more samples than most of the deeper surveys than ZTF, for example, LSST or Pan-STARRS can get because their field of views are smaller. Using those thousands of samples, what I basically do is look for periodic variations in the fluxes in these samples to identify potential gravitational wave sources. That's non-trivial, so a lot of my work has involved incorporating GPU period finding algorithms to identify these, and also building sort of custom setups to make this possible. That's my computer that I put together at work at Caltech. And this phase space has turned out to be really rich for more than just the gravitational wave sources. There are many other interesting classes of sources. One that I recently found is an analog to the white dwarf pulsar AR-SCO. You can look up the paper on that. We just published a Nature paper on another, which was a rapidly rotating merger remnant, a white dwarf that's the most massive white dwarf known. It's just barely bigger than the moon. And it rotates every 6 minutes. And it's also extremely magnetic. With a magnetic field of over 700 megagauss. But what I want to emphasize for the remainder of the talk, and really I hope to get you excited about, are that these double degenerates are just amazing. So here are the 15 of the sources I discovered with ZTF. I have many more now, actually. There are really two basic classes. There are eclipsing sources where one object transits another, and that causes an attenuation of flux. And then there are ellipsoidal variables, the more sinusoidal ones, like that 20.6 minute, which basically arise from the tidal deformation of one of the objects by the other. Basically, it's close to overflowing its Roche slope, like I mentioned earlier. And here are little movies of light curve models I've actually generated for two example sources. The one on the left corresponds to the 6.91 minute binary you see in the upper left-hand corner. By the way, I should mention that's the shortest period eclipsing binary known. It's pretty stunning to watch this thing disappear just under every 7 minutes. And the other source that I've made a model for is actually that 20.6 minute source. This is an ellipsoidal variable. Basically, the idea in the ellipsoidal variable is the denser object is tidally deforming the lower density object. And that deformation gives you a flux modulation at twice the orbital frequency because you alternate between seeing the more teardrop-shaped geometric cross-section of this deformed star to a circular one, back to a teardrop shape, back to a circle in one orbit. And that gives you two flux maxima and two flux minima. And so another part of the program, of course, in characterizing these is obtaining spectroscopy. There's a lot that one can learn from it. One is one can measure abundance ratios of elements. For example, you can see some of those sources have a lot of extra lines in them. Those are helium absorption lines. One can infer the atmospheric ratio of hydrogen to helium in these sources by basically comparing those line ratios, and also very precisely estimate the temperature because basically with helium, you've got two ionization states in the molecule, helium-1 and helium-2, and just using plain old Boltzmann statistics, you can kind of infer what the temperature of the photosphere must be based on the intensity ratios of those lines. You can infer things like the surface gravity of the object by looking how much the lines are basically pressure broadened by the gravitational exertion. And you can, of course, infer the temperature also from the lines, not just through line ratios, but basically through the width and profiles of the lines, and also the general shape of the continuum, which, of course, reflects some underlying black body approximately. The other thing you can do is measure Doppler shifts from these lines, which is extremely useful because that gives you a kinematic solution for these objects. Where you can actually start to measure dynamical masses and constrain the masses of the components in the system. But I want to talk about something a bit simpler than the complicated nuances of spectroscopy and just show you how much you can do with only a light curve. And so this is a high signal to noise hypercam light curve of the 7 min binary. And just by looking at the light curve, without even making a model, I want to show you how much you can learn from it. The first thing that most people's eyes are drawn to is there's a really deep eclipse, a total eclipse. And that already tells you several things. One is the inclination's got to be pretty close to 90 degrees, right? And you can and that's because if it were face on, it would not be eclipsing. And you can imagine by constructing a model, you can measure it much more precisely. You can actually measure it to about 1/10 of a degree. In this particular system, the measurement of the inclination is actually about a factor of 10 better than what the gravitational wave detector will be able to do. And that's pretty impressive because this is one of the highest signal to noise sources LISA will see. So it's also a great check that the gravitational wave detector is spitting out numbers as expected because the electromagnetic constraints are just far superior in this case. The other thing you can infer is actually that one of these objects is way hotter than the other. And the reason is that total eclipse is basically telling you most of the flux is coming from one of these objects. And what modeling actually lets you infer pretty precisely is the surface brightness ratio of the two objects, which is basically a proxy for temperature ratio. But there's more you can infer just by looking at the primary eclipse. And that's that one of these objects is smaller than the other. The hotter object is smaller than the other. And the reason is it's a total eclipse. So the object that's the source of most of your photons has to be completely occulted by the cooler object to get an eclipse that deep. And you can even go one step further and invoke the white dwarf equation of state and say, oh, I also know that that must be the more massive object. So it's pretty impressive that just by looking at an eclipse, you can infer all of these properties. And I'm just giving inequalities here, but you can imagine through modeling actually make pretty precise statements on all of these quantities just by modeling an eclipse. And then you can do things like in the bottom of the eclipse actually measure pretty precisely what the temperature of the secondary is. In this case, that secondary white dwarf is only 5,000 degrees and prove some cool physics, tidal physics. And the reason is there's a prediction that the white dwarf in this system should be heated to about 15,000 degrees by tides. And observationally, we see that its surface is only about 5,000 degrees. And that's a big tension in the models because a 15,000 degree black body radiates significantly more energy than a 5,000 degree black body. So it's telling us our theory is actually off by 2 orders of magnitude from the observation. But it's a subtle thing that you get from really characterizing a light curve very, very carefully. So I want to wrap things up since I'm running short on time and just say one last really cool thing you can do by modeling these systems is you can actually measure their orbital evolution there due to gravitational wave emission. And I've done this now for 4 systems, and that's by timing that eclipse. So it's again a property of the eclipse, though you can also do it with ellipsoidal systems. And basically the idea is if an orbital period's not changing and you know the orbital period, let's say it's exactly 6.91 minutes, you'd expect an eclipse to happen every 6.91 minutes on the dot. But if the orbital period is shrinking, what starts happening is that eclipse time starts drifting because it happens sooner and sooner and sooner than you expect. In the case of the 7-minute, you can see here that eclipse time is drifted by 2,500 seconds. You might say, wait a minute, 6.9 minutes is shorter than 2,500 seconds. What are you talking about? It's not that the period has changed by 2,500 seconds, is the eclipse time has drifted compared to a constant orbital period. What that basically means is this system has actually skipped several orbital cycles as a result of its shrinking period compared to a system that doesn't have a shrinking period. And I'm going to wrap up there. Thank you for your attention.